Good morning. Welcome to our second keynote. I'm really delighted to be able to introduce our speakers this morning. This is an exciting and somewhat unusual keynote in that we actually have two speakers. This reflects a really exciting collaboration in computer security research between folks at the University of Michigan and Addis Ababa University. Particularly given world events in which there's been so much activity towards separating people and building walls, I'm particularly delighted that ISCA can showcase two people who are building bridges and collaborations for the greater good. We have two speakers, as I said, and one of them is Fitsum Andargie. Fitsum is an assistant professor and chair of the computer engineering chair of computer engineering at the School of ECE at Addis Ababa University. He is also an adjunct research scientist at the University of Michigan. His interests are in security and in accelerating graph algorithms with hardware-software co-design. He received his BS, Master's, and PhD from Addis Ababa University, and he has had long-standing collaborations both with Michigan and the University of Toronto. Our other speaker is Todd Austin. Todd is the S. Jack Hu Collegiate Professor of Electrical Engineering and Computer Science at the University of Michigan, as well as the director of the CE Lab at Michigan. His interests are in computer architecture, security, and verification, among others. Prior to Michigan, Todd was a senior architect at Intel and creator of the simple scalar simulation infrastructure that many of us have used. While at Michigan, Todd has started two companies. He's also the winner of the ACM Maurice Wilkes Award and the IEEE Ramakrishna Rao Award. Without further ado, Fitsum and Todd. Let's welcome our speakers.
Thank you for that introduction. This talk is about a story. It's a story about research in the area of hardware security, but it's also a story about people, and I want to introduce you to those people. It all starts out at two different institutions in two different countries, University of Michigan in the United States and Addis Ababa University in Ethiopia, where some faculty met and decided they want to collaborate with each other. Myself, Professor Valery Bertacco, who's in the audience over there, and Fitsum. And in that process, we moved back and forth between each other's institutions and built stronger ties along the way. As those stronger ties developed, our students started to get involved from both sides. And then they traveled back and forth between these institutions to build stronger ties. We're especially grateful to our sponsors who help finance all of this, which includes companies, universities, as well as foundations. And it was all between Fitsum and I in pursuing what we're going to talk about today, zero trust architectures.
So our talk today has four parts. First, we will talk about how the global partnership between our two institutions evolved, and then we'll talk about early research that came after our collaboration. And then we'll talk about the design of the first cryptographic strings enclave that came out of our collaboration. And then finally, we will part away with some takeaways and how to get involved in such collaborations.
So let's start by looking at that first part where we're going to talk about how we develop this collaboration relationship.
So because the US does not require any introductions, I will start by introducing Ethiopia. So Ethiopia is a country in the east of Africa, at the Horn. It's landlocked, and it's mostly highlands, which explains the long-distance runners that beat in the Olympics. And it has a long history. I think some of you know the Queen of Sheba from the Kingdom of Saba. And that is a predecessor to the ancient Aksumite dynasty that ruled Ethiopia for almost 1,000 years. And we also claim to be the cradle of humanity because the first ever complete human ancestral fossil was discovered in the Hadar region of Ethiopia. The country is also home to 80 plus ethnic groups, which is a mosaic of people. We have our own script that you've seen our names spelled. And also it has a long traditions of Christianity and Islam coexisting together. And we claim to have great vegan food as well. The economy currently is growing fast. It used to be led by agriculture, but now there is a burgeoning emerging tech sector, which actually is now we're training people for. What's unique about Ethiopia is that it has never been colonized, and it's also the birthplace of coffee, and we believe that we drive the human race to success through that. We also are the source of the Blue Nile. We contribute about 80% of the waters up to the Nile, which is the longest river on Earth.
Our collaboration started in 2009, 16 years ago, when myself and Professor Valeria traveled to Ethiopia and Addis Ababa University, AAU, to meet with faculty and students. That's, in fact, when I first met Fitsum. Besides meeting with faculty and students, Valeria gave a presentation on research in University of Michigan Computer Science and Engineering. And we quickly discovered we had a lot of common interests in computer architecture and computer engineering, and a desire to collaborate more. So we left that meeting knowing we have to find a way that we can collaborate. Some of the early challenges that we had to overcome was communication between our two countries was a bit of a challenge. In addition, there was a compute capacity issue at AAU where they didn't have quite enough computing capacity to do computer engineering research.
So, deepening our ties, in 2010, one of our colleagues in our student department got accepted for a PhD opportunity at the University of Michigan. That started the chain of events. In 2011, through the support of the University of Michigan, Intel, NVIDIA, and Xilinx, we were able to set up a high-performance computing lab at AAU, and that led for other research opportunities. 2012, Professor Todd and Professor Valeria decided to come to spend their sabbatical teaching at our school, and they taught security and fault-tolerant computing courses. In 2013, a memorandum of understanding was signed between our two institutions, cementing the collaboration at the institution level. 2014, we started a program called the May program, and it's named after the month of May because the University of Michigan students finish their courses in April, and they start their research and internships in June. So we have 1 month that they can come to our school, collaborate with our students, and also teach a course, as you can see here, one of our students doing. In 2016, I was able to join University of Michigan as UMAP's scholar. UMAP stands for University of Michigan African Presidential Scholar Program. And that's me when they are sending me off.
So as this collaboration started to develop, we really honed in on, Fitsum and I, focusing on hardware security. And I want to tell you some of the background of how that came into effect. Fitsum at the time was trying to develop teaching capacity, professors and graduate students that could teach courses, in particular in computer security, because the IT sector is very hot in Ethiopia. There's a lot of infrastructure development, so there's a lot of jobs if you know security. And there was a lot of interest in the students in computer architecture, so he's trying to develop additional capacity for teaching computer architecture. I went on sabbatical there in 2012, and they asked me to teach a computer security course. I'd never even taken a computer security course, but any professor will tell you the best way to learn material is to teach a course in it. So I was teaching, for the first time, a computer security course, gathering material from all the friends I knew in that area. And I was literally 1 hour ahead in terms of knowledge of the students, which, by the way, was a big problem because it was an hour-and-a-half class. But we got through it, and I learned so much, and they learned so much. And one thing I learned is I have a true love for computer security. So as this developed, the common themes were computer architecture and computer security. So it was natural to move into hardware security. So now let's take a look at some of that early work we did in hardware security. But before we do that, I just want to take a moment to kind of set up why is security an area that doesn't seem to advance very effectively, and then why zero trust is becoming more and more interesting in that area. If you're alive and aware of your surroundings, you probably know that computer security isn't very secure. Things are getting breached all the time. That's because we really need to solve two problems to make systems secure, both of which we're not very good at solving. The first is you have to fix all software bugs. And if you're a software developer, you know that we can't fix all software bugs. Attackers use software bugs to step around the security measures inside of a program. Now, we have both heuristic and mathematical formal methods to find bugs in programs. The problem is those technologies do not scale to the size of the programs that we build. And they don't work at the rate at which new code and features are coming into these systems. So these solutions are neither sound, they don't always find bugs when they exist, and they're not complete. It doesn't find all of the bugs. And so we're always left with software that's vulnerable to attacks. Let's say you solved that problem, and you could build software that was perfect and had no bugs in it. You just have the second problem of what are called side channels. Side channels are when your system has externally visible, publicly visible behaviors, like how it accesses memory, what is the timing of a request to an API, etc. And that information reveals clues about the underlying secrets inside the system. In a computer system, those things are, what is the control flow of the program, how is it accessing the cache and memory, and how does it speculate? These things reveal lots of information about the secrets in the program. And even worse, when we try to do performance optimization, we tend to make those side channels louder. So there's a huge amount of tension in the world of computer architecture that ultimately creates these side channels. Just as a case in point on how bad we are at computer security, in the last decade, US residents have had their social security number stolen at a rate of 70% of Americans. The social security number it's like your financial key. It's a secret number that if someone can discover that number and associate it with you, they can essentially access your finances. And 70%, myself included, have had our social security number stolen in breaches.
So, how do you currently solve problems with security? So when we get attacked, we do patches, and this actually what it means is like we can always remove all the patches, all the vulnerabilities from the system, because the patches that they use to solve one vulnerability could create other vulnerabilities as well. So we cannot continue doing this forever. So Yeah. What this creates is an asymmetric battlefield where attackers require only one vulnerability to get into your system, but you as a software developer have to fix all the vulnerabilities. That is impossible. And perfection becomes the name of progress in this case, because you cannot have a perfectly secure software. So despite the many investments in securing software, a problem that was discovered in 1972 of buffer overflow still has like a ghost at the back of your mind, affecting systems. This report in June 10, 2025 is case in point. Still we have a problem and buffer overflow. So we say that progress in software security is like, not happening. So we need more solutions for that.
So because of our inability to find and fix vulnerabilities and lock down systems and make them secure, there's been a movement in the computer security community called Zero Trust trend. It's really misnamed. It's not about zero trust. You always have to trust something. But it's about moving trust away from things that are untrustworthy to things that are more trustworthy. To give you an example, when you checked into your hotel, perhaps there was a plate of cookies at the check-in desk that said, please take one cookie. Now that's a full trust system. You need to trust every person that walks up to that plate that they're only going to take one cookie. If my children perhaps were to walk up to that plate, there might be a lot less cookies on that plate after they did that. A zero trust system still has trust, but it tries to minimize the trust in the things that we can really rely on. So we're going to have a padlock on the cookies, and there's going to be one person with a key, and we're going to be able to hopefully trust that person to only release one cookie per arriving customer. So the goal with zero trust is to move trust away in computing systems from things that are untrustworthy to things that are trustworthy. So what is untrustworthy in computing systems? We've already seen software is untrustworthy because we don't know how to fix all the vulnerabilities. So if there's any trust in software, it will let you down. Programmers can also be untrustworthy. Are the programmers developing software in your best interest, their best interest, their blackmailer's best interest, or their company's best interest? You don't really know the answer to that question. So it's one of the big trends is to move away from trusting programmers. And then IT staff. On rare occasions, IT staff can go rogue, go super user, get access to your data, sell it, keep it, blackmail you, ransomware you, etc. So we don't want to trust them as well. We want to move trust away from programmers, software, and IT staff, and we want to move it to more durable technologies. What are durable technologies? They're things based on cryptography and mathematics, things that we can trust and prove that it will not let us down. This is like external monitoring infrastructure, hardware security. The thing about hardware security is there's no software in it, and advanced cryptography.
So one of the early works that we worked on as collaboration with Todd and my students, Asawi and Donham, is building an encrypted memory system called Trur. Trur in Amharic means armor. The idea is to have a highly secure on-chip memory that provides protection against cold boot attacks, bus snooping, and memory latency, memory replay attacks. It includes, it allows you to store sensitive data like your keys on-chip memory. Whenever that on-chip memory is full, you have the possibility of securely paging out, page swapping of your data to DRAM, where it's still encrypted, so you don't have any access. So a key takeaway from this work was that cryptography is a durable protection if keys are involved, and these keys are out of the reach of software.
So building on that idea of cryptography, which is very, very trustworthy, and keeping keys away from software, which is very, very buggy, we built this machine called Morpheus. It was a secure CPU. Its mission was to stop a particular attack called control flow injection. Someone is trying to get their code or your code to operate in a way they want, some external attacker. In this project, it recognizes that to make an exploit on a system, you first need to have vulnerabilities, and there's lots of vulnerabilities in the software. We always have them. And then what the attackers do is they manipulate the internal state of your program. And typically what they manipulate is the code and the pointers. So we said, let's build a RISC-V target where it's just like a normal RISC-V target, but the code is encrypted and the pointers are encrypted, and they're both encrypted with a key that software cannot access, and it's an ephemeral key. It's just picked when the machine boots. And so you've essentially made the machine a puzzle. How do I encode these pointers? Well, the CPU can encode the pointers, but an external attacker that's trying to manipulate those pointers, they can't understand what they mean. We built this machine with DARPA, and then DARPA did what's called red teaming on the machine. Red teaming is where you hire attackers to try and penetrate the machine. They worked on it for 3 months, and not a single time were we able to penetrate this machine. When we designed it, we tried to make the cryptography as lightweight as possible. Cryptography can tend to be very expensive. So for example, to decrypt the code, we put it in the front of the pipeline at decrypt stage, and so it was only exposed latency on branch mispredictions. So if we could predict our branches well, we had no latency for decrypting code. And then to decrypt pointers, we put it in the jump to a register path. So only when you executed that particular instruction did you experience that latency. And it was only a few percent slower than a normal machine. The takeaway here is that cryptography is a really durable protection, and if we're really clever about how we design the pipeline, we can keep the overheads super low.
So another work that was done at our lab is called the ACT. It's a hardware detection mechanism for raw hammer attacks on memory systems. This idea actually was conceived when Todd students came to visit us, and my PhD students started working on it. So the idea is attackers could use activations in the DRAM to effect change in other rows of the DRAM. So what we do is we've created a mechanism to keep track of rows in DRAM that are being activated continuously, and we look at a threshold, and when that threshold is reached, we move those rows to a row buffer a SRAM row buffer that we have created especially for this. So what we found out is when you move it to the SRAM, the continuous activations would not affect other rows. So this way, we eliminated the problem with row hammer. And we also tested that this is good with double-sided row hammering as well. So again, from this work, we took the idea that hardware monitoring, external monitoring, can also be a durable protection.
And then one last piece of work we'll show you before we get into our third section here is a pretty wacky design for a computer architect to look at, but it's a code injection proof CPU. I worked with my student Bill, and Bill made this really interesting observation. He said that the whole problem in the world of security exists because there's a path from the data cache to the program counter. You can look at thousands of attacks and you will traverse that path. If you break that path, you break those attacks. So he said, let's build a machine which has no connection from the data cache to the program counter. Now, as a computer architect, you'll know that means you need to get rid of 2 instructions: return and jump to a register. Can you build your system without those 2 instructions? And the answer is yes, you can. You can. So for example, look at this piece of code. This is a little function called bar here. And it returns at the end of the function. And we replace that return instruction with what we call a sled. The sled loads the value from the stack and then does if compares to the value. And if it matches, it's comparing to where you would possibly return to. That's known by the compiler. You can only return to places where you've been called. And so if you get a match, you jump direct. You do a direct jump. Direct jump bits come from the code. They come from the iCache. So you don't need that path to the data cache. Now, the attacker who needs to take their data and put it in the program counter, that path doesn't exist. The proof is basically no wires, proof, QED. And now you've built a machine where you cannot get off the control flow path. What's so amazing about this work Bill did is it was really the first effort to stop control flow injection that was both sound, it never stopped you from doing what you wanted to do, and complete. There was simply no way to get off the control path. Really amazing piece of work. Still can get hit by Spectre and Meltdown because you can speculate, but in the non-speculative path, it was really amazing. So the key takeaway to me was you can be sound and complete. You can really advance technology if you think a little bit out of the box, and if you have the ability to change the underlying machine.
So after like some time of like collaborating this way, we wanted to upgrade the collaboration. So through the initiation of Professor Todd and Valeria, that we wanted to, introduce African undergraduate students to research through 3 months, 12-week research immersion program at the University of Michigan we call Aura. The idea is to inspire undergraduate students to do research in computer architecture. It actually succeeded because about 60% of Aura students actually who applied for graduate studies got accepted. I think first 2 years, all of them that applied got accepted to prestigious universities. I think some of you may have one of those students. So this was successful because of a strong commitment from both institutions in Africa and in University of Michigan as well. However, in 2025, the program is on hiatus because of the situation in the US. So,
yeah, the situation. We're especially grateful to our sponsors. Richard Ho's been running around here from Google. He was the first sponsor to Aura from Google. Intel, ARM, the College of Engineering, University of Michigan. Bobby Monet's been running around here. She got us money from Meta. Thank you all so much. It really helps to have these resources. And the Buffett Foundation has also been incredibly generous. So we've been able to find resources. The bottleneck for us in this program really hasn't been money, it's been engagement from faculty and such in terms of the lab stuff. So it's really been a fantastic program. Okay, now let's go into the third part of the talk. We're going to look at a collaboration we've been working on for a little more than 5 years to take that zero trust in a CPU really to the next level, designing what we call the sequestered encryption enclave.
So how do you take zero trust from good to great? So what we mean by that is like, first thing you do is to concentrate trust, okay? So instead of like having a huge area of like trust, you just concentrate into, say, a trusted secure enclave. Second, we want to eliminate all software vulnerabilities. But we know that there are, because vulnerabilities in software, it is hackable eventually. So what we do is we want to remove software from the enclave, from the trusted enclave. Third, what we want to do is how do we silence digital side channels? Because we are computer architects and hardware architects, we know how to do that. So we can create provably side channel free enclaves. First, we've seen that cryptography could be a durable solution. So we eliminate trust for all remaining hardware and software in the system, and encrypt data and everything else outside of the enclave. So this led to a creation of an enclave called sequestered encryption. It's a hardware-only enclave without software vulnerabilities or digital side channels, and it computes directly on data, encrypted data.
This idea of computing directly on encrypted data, it's a really, really powerful concept. It essentially makes hacking not useful. The goal of the hacker is to become as powerful as the programmer. But when the program is operating on encrypted data, the programmer cannot see the data. So becoming as powerful as a programmer doesn't buy anything. It's a really powerful concept. And what we've learned in this work, that really the key to better security is just a functional unit. It's a special functional unit that can process encrypted data. In the program, there'll be some decrypted data that we don't care about its protection. And then there'll be other data like our social security numbers and other secret information that'll be encrypted, and that information will be processed by a specific functional unit that handles encrypted data. Now that specific functional unit will use the same concept we talked about earlier. It'll sequester a key inside of it that software cannot access. And it'll use RISC operations. Add these two encrypted values together, give me an encrypted result. Add this encrypted value to this non-encrypted value, and give me the result, encrypted, of course, and et cetera, et cetera. So it's just a RISC interface to it. There's no software in the box. It's just instructions accessing it. How do we get that key safely into the functional unit? Well, fortunately, that problem was solved in 1976 when Whitfield Diffie invented public key switching. So essentially, we provide a public key to a functional unit in your pipeline, and a third party or an IT operator can inject a key into that box, and no software can see that key. Once that key is in the box, there's just encrypted data flowing into the functional unit, it's decrypted, it's processed just like a normal functional unit, and re-encrypted and comes out. When it's outside in the rest of the box, it's encrypted under high entropy encryption. That means it looks like pure random data. If you encrypt 1,000 ones, you get 1,000 different ciphertexts out of it. And it's integrity checked. So if somebody manipulates that data, we'll know about it the next time it comes into the box. So everywhere outside of that place, there's no trust. We know the cryptography is protecting that data. There's no trust in the software. There's no trust in the rest of the hardware. Just, as Fitsum mentioned, we've concentrated that tiny little functional unit box. And you can do this within 20% of native execution speed.
So, you cannot trust us when we say, like we have created this trustworthy hardware. To ensure that that its security is good, the enclave was provided to red teams called the Blue Bastion red teams to test it and to see if there are any vulnerabilities in that. They tested it for 3 months, and they could not find any vulnerabilities. So zero vulnerability. However, what does it mean when a red team could not find bugs in it? So what it means is that they couldn't find any. It doesn't necessarily mean that there are none. So because we could not trust that, this was again exposed for a formal verification. And this work was done in collaboration with Princeton, Sharad Malik's group, and it was formally verified, and they identified that the enclave implementation is bug-free. No vulnerabilities were found, and that work was awarded at ISCA'25.
Now, when information you're processing is encrypted, attackers can't see it, programmers can't see it, IT staff can't see it. So we've built that, we've moved trust away from those three entities. But when programmers can't see it, you can't write a data heuristic program on information you can't see. They actually have to write what's called a data oblivious algorithm. A data oblivious algorithm is an algorithm whose behavior is independent of the inputs of the program. If you think of like matrix multiplication, you don't change the way you do matrix multiplication based on what you're multiplying, right? So that's a data oblivious algorithm. In fact, a lot of algorithms from linear algebra and graphics and AI are already data oblivious naturally, so that's a great. But other things like, anything recursive would not be data oblivious. So you have to convert those algorithms to be data oblivious. Fortunately, in the 70s, they proved that you could build a data oblivious Turing machine, so any program can be data oblivious. The way programmers make their programs work with encrypted data is they decide what part of my program do I want to protect, and they change those variables to encrypted variables. So, if a variable is in a UN64, it's not protected. If it's in a encrypted UN64, it's protected. And then you just use it in your language just like you normally would. You just operate on it. There's a few caveats, though. If you want to make a decision on a variable, you have to generate an encrypted predicate, true or false, and then you have to use a predication operation, a conditional move, where you've evaluated both the true side of the if statement and the false side of the if statement, and then you just select the result. You can't have an if statement on an encrypted variable predicate because you don't know what the value of that predicate is. And if you could, you'd have a side channel too. And then second, if you want to index a RAM with an encrypted variable, use that as an index, you have to use what's called an oblivious RAM, where essentially you scale the entire RAM. So certainly if you're doing things like that a lot, you want to redesign your algorithms to not do that. To help developers create these very special programs, we developed the octal compiler, which essentially validates that the program you're writing is data oblivious and then tries to make suggestions on how to make it as efficient as possible. And then like any good computer architects, we've got to produce a benchmark suite. And we've done that in the VIP bench, very important privacy benchmarks. These are all benchmarks, 42. They can either run in their original data heuristic mode or in a data oblivious mode or in full encrypted mode. And we use this benchmark suite to compare sequestered encryption, our technology, to other frameworks that do encrypted computation, like homomorphic encryption or multi-party computation. So we can make those comparisons readily.
So we want to show you like one application of this SCE enclave. So like many of you may have surveillance equipment at home looking at your backyard, and that data is streamed to the cloud for processing. And for example, that processing could be going through an ML or AI pipeline to check if there are any residents appearing, intruders, or animals. And that message is sent to you as an alert. But through this pipeline, the people in the cloud could be looking at your data because they can decide, because it's not encrypted, they could decide to access it and do whatever they want with it, and they're happy about that. What SE could do is, when the data is streamed to the cloud, it is encrypted, And when it gets processed in the cloud, and when it was given to the ML pipeline, it is still encrypted, and the result that is sent to you is still encrypted, right? We don't know what the outcome is, because you are the only one that holds the key. You should be able to receive the results. So the people in the cloud do not have access to your data.
All right, so that's our story. Let's close it up now with just a few takeaways and then some thoughts on how you might get involved in a collaboration like this.
So, what did we experience through our collaboration? The first one is diversity. What I mean by diversity is diversity of thought, diversity of culture, and diversity of background. This creates a fertile ground for innovation and collaboration. I can tell you of an experience I had when I visited Todd's lab in 2016 through the UMAPS program. Then I was finishing up my PhD, and I was working on a problem, and it's been frustrating me for a long time because I couldn't figure out if I have made progress or not, and I was not. Anyways, what happened was one of Todd's students comes over to me and he was just asking me what I was working on. I was just telling him, and he points out that, do you know that computer has a GPU in it? And I was like, really? Yeah, can I use it? And then I used that GPU. And when I was using that GPU, what it allowed me was to think that I could test the algorithm I was working on with bigger data. And turns out the problem was solved a long time ago, but I was not testing it with the data that I was supposed to, because I was building this algorithm for a mobile phone. And I was stuck there. So this simple example is, I think, what most of you are experiencing when you work with people across boundaries. They help you with identifying problems with your current situations and help you innovate. Another one that take away from our collaboration is you make the connections strong by working with people, by connecting them at the human level. For example, if you create, for example, if you meet regularly through email, through virtually, and that keeps the connection strong. And this tends to, grow your collaborations. And what I've seen that people make mistake is that they rush to institutionalize the collaboration, and it dies on that paper. So that has been my experience.
And something I've learned over the last 3 decades working in computer architecture. For a while in the 2000s, I was working with students from Cyprus. And there were not a lot of schools discovering students from Cyprus, but I found they were pretty amazing. And then in the 2010s, I started working with students from Ethiopia. And not many people were discovering students from Ethiopia, but I found they were really amazing. And it really occurred to me that, brilliant students are everywhere. But the opportunities, the pathways to success, as we call success, going through undergraduate higher education to pursue the career of your dream, those pathways are really deep and hard to get out of, right? But if we can create new pathways, you will find brilliant students. I mean, my research group is 75% Ethiopian. I love working with Ethiopian students. They're fantastic students. So a true, something I really found quite striking. And then another thing I've been saying for the last decade is when you get to the fork in the road, don't ask yourself, what's the best utility? Which will advance my career the best? Just ask yourself, what has the best adventure? When I went to my sabbatical decision, I could either go work with Fitsum for a year teaching. Who wants to teach on their sabbatical, right? A class you've never taught before. This seems like the worst sabbatical ever. Or I could go work for a company. But I thought, like, what adventure it would be to get a chance to live in Africa. And it was true adventure. It was so amazing. So, I'll just recommend, think about that. What is the more adventurous path you can take? And it'll really make your career more engaging and more rewarding. I'm quite sure of that.
So we want to leave you with like some of our experiences to help you, like how to get involved in these kind of collaborations. Like I was saying earlier, make and grow the connections. Come visit. Let's have coffee. If you come to Ethiopia, you will have the best coffee ever. So I do invite you for that. Come teach courses, and the same thing. We come to you, and we also collaborate in that level.
Yeah, and then look for funding opportunities to take advantage of these particular situations, to start new collaborations with new spaces. NSF has long had programs, well, maybe not anymore, but they've long had programs to support, development of research collaborations with Africa. And there's many foundations, the Susan G. Buffett Foundation, the MasterCard Foundation, will support these activities. And we found literally that the money was waiting for opportunity rather than trying to figure out who to send it to. It's just, these paths don't get created very often. So if you can build these paths, there is support out there to let them grow.
Just recruit the students that you collaborate with, and you would see that they would do really well. The Aura pipeline has been very great in the way that undergrad students get interested in doing research in computer architecture and related fields, and we've seen that it works really well. So I say, and we say, recruit students from your collaborators and see how that pans out, and we believe it really does well.
And if you want to collaborate with us, just reach out. We'd be glad to do that. We can set you up. Visit Ethiopia, amazing place, teach a class. You'll never regret it. So please reach out if you're interested. And then finally, we just want to say thank you.
Thank you.
These are some of the students that have come through the program, some that have come through our activities, but also additional students that have come through other departments as well as working on non-hardware security related, and where they've ended up. So thank you so much.
Thanks to both of you for an inspirational and very interesting talk. Are there any questions from our audience? Please come up to a microphone.
Natalie Enright-Jurger, University of Toronto. Thanks, Todd and Fitsum. This was really great. What role can professional societies like ACM SIG-Arch or conferences like ISCA play in fostering these kinds of collaborations? Do we need to be bringing our conferences to more diverse places, bringing more diverse folks to our conferences? How do we support this?
Come to Ethiopia and host ISCA.
We would love to bring one of the major conferences to Ethiopia.
Actually, I think at least ISCA, I know, is doing well because of the UARC program. When the first time that invitation was sent to me to introduce it to our students, I sent it to a few of my students, and they applied and they got accepted. And when they came back, they were so excited about the opportunities that they were exposed to, and they were very happy. And so the next year, when the invitation for me to distribute came, I was eager and I distributed. And I think that year about 4 of our students and mostly my students came here. And they were very happy, and I think that kept on. And some of them have gone into graduate studies, specifically research on computer architecture. So do what you're doing right now. It's good. And we have like a bunch of them here, right? Like I have 3 Ethiopian students here with us like working. So I think this is good, and continue with that. And please come do it in Ethiopia. Like I will help arrange.
I would also add, the traditional ways we evaluate students don't always work in this context. And I found the best way to find great students at these institutions is to, build a strong relationship with the faculty and the staff, and then really take their advice on who to work with. And that, to me, like Doniam, we saw Doniam here earlier. This is what you gotta work with this guy. He's amazing. And then he comes to Michigan, and he's one of those grad students like passing everybody, more papers than anybody. He's just making all the other students nervous. Incredible student to work with.
Okay, it's working today. First, thanks for the talk. Let me share an observation. Your team's working culture is the complete opposite of what you're technically aiming for. Like, you are all together, connected, full trust, but you're working in a system that each part is like, I don't know about you, man. Like, complete opposite. Let me come to the question. I was wondering, because you have shown examples of the work and some testing systems. How close, sorry about asking about the negative, but how close are you to putting together the whole pipeline and showing some like even simplest proof of concept? So what are the missing parts? And please think about the question about like job opportunities at your team, okay?
I have a startup at Gita Labs, which has deployed this technology into Amazon, AWS, and Microsoft Azure. It's there, it's available commercially. What's missing is a little less attention on AI. Security right now is in a bit of a doldrum. And people need to care about privacy more. That's also very important. Yeah, I think technology is there, just the desire for society.
Okay, so you could put the technology together and do like data center. It could be slow, but it would be working, like trustless data center processing, yeah?
Yeah. Whenever I go to, when I talk about this technology to any CPU or GPU vendor, I always ask them the question: when's the last time you added 190,000 gates to your design and it changed the relationship with your customers? This is powerful technology, but people got to want it. So thank you.
Yeah, thank you very much.
Moin Qureshi, Georgia Tech. Amazing collaboration. This is an example where the intellectual merit is very high and the broader impact is also very high. So you're right that AI is getting a lot of attention and money. There's another area that's getting money, right? Fully homomorphic encryption. Looks like your technology is achieving what FHE tries at very low cost. What are the trade-offs? Why would somebody do FHE instead of this? And shouldn't there be more money than into a technology that costs less?
So I get this question all the time, and the way I explain it is like, FHE is the way a mathematician solves the security problem, the privacy problem. This is the way a microarchitect solves the security problem. This is the trade-off. FHE has no hardware vulnerabilities. This technology has an analog side channel. Fitsum kept saying digital side channels, this is timing-based side channels. Has an analog side channel. If somebody wheels an electron microscope into the Azure data center, they can get your data out of it. The trade-off, though, is this is 100 million times faster than FHE. All the FHE we see in this conference is integer FHE. That is punch in the face, hard to program. The true FHE is Boolean FHE. It's Turing complete. And it's what you see 10 to the 6 slowdown for integer FHE. you see 10 to the 9th, 10 to the 10th slowdown for Boolean FHE. So, we call this consumer grade privacy. And that's how we really like to sell it. And if you have to ensure that nobody can put an electron microscope on your design, then you'll always have FHE to worry about.
Thank you.